Hello, welcome again to noise control and its management. Today is the 5th day of this particular week, and what we plan to do today is very quickly in next 4-5 minutes develop the solution for the one dimensional velocity wave equation for spherically propagating waves, and later what we will do is develop a relation for complex impedance as it relates to spherically propagating waves. So, we had shown that the solution for one dimensional pressure wave equation is P R T equals 1 over R real of P plus E j omega t minus R by C. Okay. So, this is the solution, and this is the solution, this is a valid solution as long as there are no reflecting surfaces around the source. And because the nature of the equation for velocity, see this is the velocity pressure wave equation, and if we develop the velocity, this is the pressure wave equation, and if we develop the velocity wave equation, it will come in exact same form. So, with that understanding, I can directly write that velocity for spherically symmetric waves when there are no reflections could also be expressed as u plus E j omega t minus R by C. And now our concern is how are P plus and U plus mathematically related, and the answer to that will come from the momentum equation. So, now our aim is to find relationship between P plus bar and U plus bar. And what are those P plus bar and U plus bar? Actually, I will write them. So, that is separately. So, what I will do is I will define what is P plus bar and U plus bar. So, from this I get P R T equals real of P plus bar P plus over R E j omega R over C negative of that times E j omega t, and this entire expression I call P plus bar. Okay. Similarly, U R T equals real of, so I can, I am sorry for this confusion, but I will make it more explicit. So, this is equal to real of P plus bar, which is a function of R and omega times E j omega t, where P plus bar is what? So, this entire thing is P plus bar. Okay. This entire thing is P plus bar, and what P plus bar represents is the amplitude of the wave at location R. P plus represents the maximum amplitude for all locations. P plus bar represents the amplitude of the wave at location R, because it changes from place to place. So, that is there, and similarly U R T is equal to real of U plus over R E minus j omega r by c times E j omega t, and that equals real of u plus bar r omega times E j omega t. Okay. So, let us call this equation 1 and this is equation 2. Now, what our aim is to figure out the relation between p plus bar and u plus bar, and we have understood that p plus bar r omega is this entire thing encircled in green and u plus bar r omega is this entire thing which is circled in green. So, we want to find out the mathematical relationship between the complex amplitude of pressure and the complex amplitude of velocity at location r. That is what we are interested in. Now, this relationship we will be able to figure out if we use the momentum equation, and 2 days back we had developed the momentum equation for one dimensional spherically propagating waves as. So, what is the momentum equation? Was first derivative of pressure with respect to r is equal to minus rho naught del u over del t. This is the momentum equation. This is the momentum equation. So, let us call this equation 3. So, what we will do is we will plug 1 and 2 in equation 3 and that will help us relate the two things. So, what we do is we put 1 in LHS of 3 and 2 in RHS of 3 to get, and then we do all the mathematics and this is what we get. So, I have to differentiate pressure with respect to r. So, I use this equation and I put it on the left hand side, and on the right hand side I have to differentiate velocity with respect to time. So, I use the second equation and put it there. So, what do I get? So, what we get is, so first we will differentiate pressure with respect to r. So, pressure with respect to r is E times j omega t times. So, first there is a p plus divided by r term, and if I differentiate with respect to r I get minus p plus by r square E j omega r over c, and then I also have to differentiate the exponential form. So, that is p plus divided by r and minus E minus j omega r by c times omega over c, and this is the left side, and of course, there should be a j also, and on the right hand side I have minus rho naught. So, this is minus rho naught times partial of u with respect to time. So, the time component is only e to the power of j omega t. So, I have u plus over r e minus j omega r over c times e j omega t times j omega. So, this is what we. Now, I make some simplifications. So, I see that E j omega t is present on both sides, it is common to both sides. So, they cancel out each other. The second thing is that there is E j omega r over c in each term on the left side as well as on the right side. So, E j omega r over c e to the power of j omega r over c e to the power of j omega r over c, they all cancel out each other. Okay. So, what I am left with real of minus p plus over r square plus p plus over r j omega divided by c equals minus rho naught real of u plus over r times j omega. I can remove the real operator from both the sides, and also this negative sign goes away from both the sides. So, there is a negative sign here and there is a negative sign here. So, they get cancelled out. Also I can remove the real operator from both the sides, because this equation has to be valid for all values of r, not for some particular value of r. So, that will be true only if the parameters in parenthesis themselves equal each other. So, I can write from this, I can write p plus over u plus equals j omega over r times rho naught divided by 1 over r square plus j omega over r c. So, the r in the numerator and r in the denominator, they also get cancelled out. So, what I am left with j omega rho naught divided by 1 over r plus j omega by c. Now, this is also same as p plus bar over u plus bar. And why is it? Because when you see, this is the ratio of p plus over u plus. If I multiply p plus and also multiply u plus by this term, e minus j omega r over c divided by r, I will get p plus bar. And if I multiply u plus by e minus j omega r over c divided by r, I will get u plus bar. So, the ratio of p plus and u plus in our case is same as the ratio of p plus bar and u plus bar, and this we call impedance for the spherically propagating wave, and it changes with r and omega, it changes with r and omega. Okay. So, I can say that impedance, specific acoustic impedance for a spherically propagating wave, outwardly propagating wave, not wave which also has a reflected component, it changes with r and omega, and that is equal to what? It is equal to j omega rho naught divided by 1 over r plus j omega over c. And if I do the mathematics, I make this a little more simple. So, I get j omega rho naught r c divided by c plus j omega r. So, this is one form for z. I can also mathematically manipulate this further. I can say that z of r and omega equals, so what do I do? I divide the numerator and denominator by j omega rho naught r c. So, what do I get here? 1 over j omega rho naught r plus 1 over rho naught c. This is another form, okay, and this can be written as 1 over j omega rho naught r plus 1 over z naught inverse. Why, and what is z naught? Z naught is rho naught c. It is the characteristic impedance of air which we had defined earlier. So, we have two mathematically equivalent expressions for z. So, we will just write it. for purposes of clarity. One expression is j omega r naught r rho naught c divided by c plus j omega r, or I can also express it as 1 over j omega rho naught r plus 1 over z naught inverse. Now, we make some important observations at this. So, this Z is the specific acoustic impedance for spherically propagating waves where there are no reflections, So, if there are no reflections, these waves continue to travel outwards and go up to infinity and never get reflected back, and their specific acoustic impedance is defined by this equation, and it depends, the specific acoustic impedance, it depends on omega and it also depends on r, right. So, now we will make some observations. So, the first observation is that for a one dimensional wave which was travelling in a Cartesian frame of reference, say for instance in a tube, we had found that its specific acoustic impedance, if the tube is infinitely long, if it is infinitely long, there is no reflection. For such a tube, we had found that its characteristic impedance Z naught and its specific impedance were same, but in this case Z r omega is not equal to Z naught, unlike that for 1D waves in Cartesian frame when there are no reflections. Okay. This is first important observation. So, spherical waves, even though there are no reflections, if there are no reflections, they behave differently compared to linear waves, waves travelling in a straight line. Second thing, we will work on the second relation thing. So, what happens when r is large? What happens when r is large? When r is large, and what do we mean by large? R is large in the sense that this term is, if r becomes very large, this term becomes very small compared to 1 over Z naught. So, what happens when r is large? So, I can say that that is when omega rho naught r is very large compared to Z naught, and Z naught we had defined it as rho naught c. So, I can also say that omega r is extremely large compared to c, or what that means is 2 pi f times r is very large compared to c, or equivalently I can say that r is very large compared to c over 2 pi f, and what is c over f? F is the frequency. So, or I can say that when r is very large compared to c over, no excuse me, so c over f is lambda, wavelength, lambda over 2 pi. So, if r is large in the sense that r is very large compared to lambda over 2 pi, so what, so if r is very large compared to lambda over 2 pi, then Z of r and omega, it is approximately equal to Z naught, because this term becomes negligible. So, what does this mean? Physically what it means is that suppose there is a point source which is emitting spherically symmetric waves and you are going very far away from it, and if you are very far away in the sense that you are several factors distant compared to lambda over 2 pi, then the waves, the sound waves which are being emitted by this source will be similar to one dimensional waves moving in a straight line, because the impedance of a one dimensional wave moving in a straight line is Z naught. Okay. So, how is it important for people who are working on noise? What that means is that if you are far away from the source, then if you are interested in managing that noise, you have to manage the noise in a sense that it is of a similar nature as that of a one dimensional wave moving in a straight line. This is the second important thing. And the third thing is, when r is small, and what do I mean by small? That is, r is very small compared to lambda over 2 pi, then now we look at this expression once again. So, if r is small, then this term 1 over Z naught will be negligible compared to this term, okay, because r is small. So, denominator is small, and if denominator is small, then 1 over Z naught can be neglected. So, in that case, then Z of r and omega, you can approximate it as j omega r rho naught. This is the other one. So, these are some of the important characteristics of waves which are travelling in a radially symmetric fashion, and tomorrow, which is the last day of this week, we will continue this discussion, and we will also do probably something similar in the next week also. First couple of lectures we will continue our discussion on spherically symmetric waves. Tomorrow specifically we will be talking about a new concept called volume velocity, and this is a very useful concept, especially for people like you who are interested in understanding noise of surfaces, noise coming from surfaces which are vibrating. So, we will introduce a new concept called volume velocity, which will be very useful for noise engineers. So, thank you, and I look forward to seeing you tomorrow. Bye.